The damp, pre-dawn chill of December 16th, 1944, hung low over a forested ridge near Monschau. Snow clung to pine branches. The ground cracked as soldiers scuffed through frost in a frozen, unremarkable clearing beyond the tree line. The crews of the 406th Field Artillery Group stood tensely beside their 6-inch howitzers. The steel of the barrels glinted faintly in lantern light. Inside their ammunition huts, sealed crates marked POZIT lay shells unlike any they had ever fired. Colonel Oscar Alfred Axelson, commander of the 406th, surveyed the ridge map spread across his command tent. Radio crackled with urgent calls from forward outposts. Men of the 38th Cavalry Squadron were in danger. Lightly armed, dug in among the trees around Monschau, and rapidly being overwhelmed by German infantry surging through the Ardennes forest. The cavalry's voice was edged with panic. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Axelson exhaled slowly, the breath visible in the cold air. The shells in those crates had not yet been approved for use over land. Their fuse, a top-secret innovation, decades in the making, was still under the highest security classification. If one failed to detonate, and German engineers recovered it, the consequences could echo far beyond this ridge, but the lives of the men under fire left him no choice. With a firm, low voice, he said, "Load POZIT shells, 0618, fire when ready." Moments later, rounds shrieked overhead. Instead of crashing into the ground, bursting uselessly, they detonated mid-air, air bursting at about 30 feet above the snow-dusted forest floor. Within seconds, the undergrowth erupted in a deadly rain of metal fragments. Foxholes, log bunkers, anything offering cover were shredded. The German advance faltered. The 38th Cavalry's calls turned from fear to stunned relief. German infantry, trained to take cover against shells striking the ground, never from above, were caught in the open. In that instant, at 0618 hours, the hidden fuse changed war. The Germans had met a weapon they did not know existed. A fuse no longer set by man's hand, but triggered by the warhead's proximity to its target. And for the soldiers watching the lethal blossoms of snow and fire in the pre-dawn woods, the war would never look the same again. By late 1944, the war in Europe had entered its final, brutal phase. More than 5 years since the invasion of Poland, the Axis had been pushed back, yet the outcome remained uncertain. The German army, battered, undersupplied, but still savage and capable, launched a surprise offensive in the Ardennes forest on December 16th. At the time, the dominant artillery doctrine across the armies of the world was still inherited from the First World War and refined during the interwar years. Artillery batteries fired shells with either contact fuses, rounds that had to strike something directly to explode, or time fuses, set manually before firing to detonate after a fixed interval. These fuses had serious limitations. Contact shells often buried themselves in the ground or struck the tree canopy or rocks and failed to achieve lethal fragmentation. Time-fused shells required accurate estimates of flight time. Miscalculate by a half second, and the shell might explode too high, too low, too soon, or too late. In dense forests, among trenches, or when facing fast-moving infantry or aircraft, these methods proved increasingly inadequate. Even before the war, gunners and engineers recognized the dream, a shell that could detonate when close enough to kill, automatically, but the challenge was immense. Mounting a sensor inside a shell required electronics durable enough to survive extreme forces. An artillery shell launching out of a gun barrel would endure accelerations of thousands of times gravity, then spin at hundreds or even thousands of rotations per minute. Traditional vacuum tube electronics would shatter instantly. Yet, the dream persisted. And by 1940, against a backdrop of global war and scientific urgency, that dream was handed to teams assembled under the National Defense Research Committee, NDRC, led by physicists such as Merle Tuve and engineers from the National Bureau of Standards. They began what would become one of the most secret and consequential technological efforts of the war. By mid-1942, the first functioning variable time, or VT fuse, a self-contained miniature radar transmitter and receiver, had been test-fired from a naval 5-inch gun. Within weeks, the 5-inch VT shells performed flawlessly. Drones simulating Japanese dive bombers were destroyed in rapid succession by anti-aircraft fire. The results stunned naval officers. Over the next 2 years, the fuse program expanded dramatically. Tens of thousands of proximity fuse, or VT or POZIT as the codename went, came off production lines, built with glass vacuum tubes ruggedized to survive the forces of artillery launch, with chemical batteries activated by the shock of firing, safety devices to prevent premature detonation, and aerial antennas built into the shell body itself. But strict security remained. Allied command feared that if a dud shell fell into enemy hands, the technical secret of the fuse, essentially a radar miniature, might be compromised. For years, the new shells were restricted to use over water. The Navy deployed them aboard ships to shoot down Japanese planes. The British used them on coastal defenses against the German V-1 flying bombs. Over land, especially in Europe, their use was forbidden. For British anti-aircraft batteries along the coast, the effect was dramatic. By the autumn of 1944, they were shooting down nearly 3/4 of incoming V-1 rockets. What had once been near-hopeless barrages of timed shell volleys were now deadly, efficient bursts of shrapnel triggered by invisible radar, swiftly, silently. Yet on land, in the forests of the Ardennes, in frozen villages, in the muddy fields of northern France, artillery remained orthodox. Shells struck the ground, exploded poorly, or flew too high or too low. When armies massed, they still relied on volume over precision. Then came December 16th, 1944. The German offensive in the Ardennes, later known as the Battle of the Bulge, was a last, bitter gamble. Surprise, speed, and a deep forest offered cover. Once through, the Germans hoped to reach the Meuse River, disrupt supply lines, and threaten toward Antwerp. Lightly armed reconnaissance and cavalry units were among the first to be swept up by the assault. The 38th Cavalry Squadron found itself alone, outgunned, in snow-choked woods near Monschau. Their radios screamed for help. "Infantry closing in. We can't hold. Need immediate fire support." At the 406th Artillery Group headquarters, Colonel Oscar Axelson hesitated. Overhead, in those sealed crates, lay the future of artillery, but orders from high command forbade their use over land, a restriction born of fear, not fear of death, but fear of technological compromise. Some officers argued waiting for formal permission, others feared the unknown. Axelson made the decision no regulations could contain. Within minutes, batteries loaded the new shells, guns roared, rounds soared, arced and detonated above the treetops. In their concealment, German infantry didn't hear the shells strike. Instead, a sudden, invisible threat struck from above. Shrapnel rained through branches, tore open foxholes, shredded limbs of trees, and severed cable, wire, and bone alike. Preparing and narrating this story took us a lot of time, so if you're enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The effect was instantaneous and catastrophic. The German assault halted. Survivors fled, scrambled, surrendered. The lightly armed and outnumbered 38th Cavalry held on. The first combat use of VT artillery shells on ground troops had shattered tradition. What followed was swift. Within days, by December 19th, the embargoes were lifted. Higher command, including Dwight D. Eisenhower himself, recognized what had happened. The proximity fuse was not just a naval or anti-aircraft novelty, it was a generational leap in artillery technology. From that moment onward, Allied heavy artillery would rarely fire without it. To understand why this overlooked fuse was so revolutionary, one must grasp the engineering miracle it represented. A proximity fuse had to be a fully functional radar set, transmitter, receiver, power supply, tiny enough to fit into the nose of a standard artillery shell. When the round fired, the initial acceleration and barrel rifling would generate 10,000s of G, forces that would shatter conventional electronics. Vacuum tubes, glass, wiring, batteries all had to be redesigned for durability. The fuse also had to remain safe until after the round was fired. Early versions used a battery that only became active once the shell was in flight, often by breaking a glass ampule that released electrolyte, powering the device. Receivers and transmitters had to be tuned to emit a continuous radio signal. When that signal reflected off-ground, trees or enemy troops, the return trigger would detonate the shell at the optimal burst height. In effect, when a shell passed within lethal range of any obstacle, no matter where, the fuse triggered. The battlefield became three-dimensional, no longer just where the shell landed, but where it passed. Forests, trenches, foxholes. Nothing was safe. But all that science, all that effort, might have remained unused, or used only in the seas or skies, without the decision made on that frozen ridge near Monschau. In those early hours of December 16th, 30-foot airbursts over snow and trees, the hidden power of the proximity fuse revealed itself. Over the coming days and weeks, its effect would ripple through the battle. German infantry, trained to brace for ground impact and time-fused barrages, found themselves vulnerable to invisible airbursts. Communications lines were severed, morale faltered. In the dark, amid the terror of shells bursting overhead, some German units reportedly panicked and surrendered rather than risk another volley. For Allied commanders, the fuse became a force multiplier. Fewer guns, fewer shells, far greater lethal coverage. What had once required massive concentration of guns and lengthy barrages now needed only carefully placed batteries and well-timed volleys. By the end of the Battle of the Bulge, as winter gave way to thaw, historians would look back and note that the VT-fused shell, once a hush-hush secret, had inflicted casualties and disruption on a scale comparable to any single battle or unit action. For many soldiers, the funny fuse became synonymous with survival. For many German veterans, it remained a phantom horror, an enemy they never saw, only felt. As dawn broke on December 17th, in the cold light over the Ardennes, Colonel Axelson stood again by the ridge map, where before his men feared being overrun, there now lay hushed confidence. The forest was still dark, snow dusted the ground, but the enemy was no longer safe. In every wood, every slope, every shadow, Allied artillery now held invisible eyes, and when they opened fire, they would punish not just where shells landed, but wherever enemy troops were. The hidden fuse had done more than save a cavalry squadron. It had changed the rules of war, and for thousands of soldiers, American and German alike, it would change everything. The morning after the first VT rounds had detonated above Monschau, the forest was eerily quiet. Snow crunched underfoot as gunners checked their howitzers, testing mechanisms and recalculating firing solutions. What had seemed impossible only days before, shells that detonated above enemy positions automatically, was now a tangible reality. Axelson walked among the men, inspecting the weapons and ammunition, noting minor imperfections that could become critical in battle. Each shell was a marvel of engineering, but it was also unforgiving. One mistake in loading, one cracked tube, one improperly secured battery could mean disaster for the crew. The stakes were palpable. This was not theory or training. This was war. The VT fuse, or POZIT as it was sometimes referred to in code, had been engineered with multiple safety mechanisms. Before firing, it remained inert. A mechanical safety prevented the fragile vacuum tubes from activating until the tremendous acceleration of the gun's firing would engage the internal battery. When the shell left the barrel, the battery would activate, powering the tiny radar transmitter and receiver. The round would then travel, spinning at hundreds or thousands of rotations per minute until it passed within a lethal radius of an object, a tree, a foxhole, or the body of a soldier, and detonate. It was a combination of precision engineering, physics, and sheer ingenuity. The engineers who designed it had solved problems that seemed insurmountable. Vacuum tubes reinforced to survive 20,000 times the force of gravity, circuits shielded against vibration and heat, antennas robust enough to function despite being twisted and spun at incredible speeds. Meanwhile, German troops had no idea what had struck them. In the aftermath of the initial barrage, survivors described a phantom threat, shells that seemed to explode above them without warning, killing comrades in positions that had been considered safe. Traditional artillery tactics had relied on the enemy taking cover in trenches or dispersed formations. The VT rounds made these assumptions obsolete. Soldiers who had trained for months, even years, to survive barrages found themselves helpless against an invisible adversary. Psychological stress increased dramatically. Fear became amplified, not just by casualties, but by the unpredictability of the attacks. Soldiers were never certain whether a shell would strike the ground or hover in midair before detonating. Accounts from German veterans later revealed a mix of confusion and terror. Some refused to advance, while others dug deeper, only to be caught in midair detonations that shredded their positions. The American artillerymen, in contrast, quickly adapted to the new technology. The fusion of science and battlefield tactics allowed them to rethink artillery deployment entirely. Concentrated volleys no longer required precise, sequential firing. Multiple batteries could engage the same target simultaneously. Forward observers, who traditionally had to carefully time each call to avoid missing dispersed infantry, now had the confidence to call coordinates knowing the shell would detonate in proximity to the target. This efficiency meant that fewer rounds were needed to achieve the same or greater effect, reducing the logistical strain on supply lines and allowing for sustained operations under harsh winter conditions. This operational advantage was compounded by the fact that Allied commanders initially withheld the full extent of the VT program from frontline troops. The first deployments in the Ardennes were limited, testing both the technology and the psychological effect on enemy troops. Commanders like Axelson had to make split-second decisions when and where to deploy the shells, balancing the risk of revealing the secret with the need to save lives and hold positions. In many cases, the decision fell to individual officers on the ground. Their willingness to act decisively under ambiguous authority became a key factor in the success of the initial VT deployment beyond Monschau. The impact of the fuse rippled through the broader battle. Artillery units equipped with VT shells began to systematically disrupt German movements. Columns of infantry attempting to advance through forested paths were met with unpredictable bursts. Armored vehicles, while resistant to fragmentation, were slowed and scattered when accompanying infantry fell. The psychological pressure alone slowed the German timetable, forcing commanders to reconsider their plans and ultimately contributing to the failure of the larger offensive. Tactical doctrine had assumed that enemy troops could adapt to artillery by dispersing or taking cover. The fuse rendered these adaptations ineffective, forcing a paradigm shift in battlefield thinking. In the months following the initial deployment, the US Army rapidly integrated the VT fuse into all relevant artillery units. By January 1945, batteries across Europe were equipped with the technology, and reports from the front highlighted both the lethality and reliability of the fuses. Training manuals were updated to reflect the new procedures, emphasizing the importance of battery coordination, proper shell handling, and the tactical use of airburst patterns to maximize coverage. The speed with which the technology transitioned from secrecy to frontline utility was unprecedented, a testament to the coordination between engineers, production facilities, and combat units. The engineers who had developed the fuse were keenly aware of the battlefield consequences. Back in the laboratories of the National Defense Research Committee, teams tracked reports from Europe with a mixture of pride and anxiety. While their goal had always been to create a weapon that would save Allied lives and hasten the end of the war, they also recognized the destructive potential of their creation. Memoirs from engineers like Robert Broad and Lloyd Berkner reflect a recurring theme. The fascination with solving a technical challenge coexisted uneasily with the knowledge that the solution was a tool of death. The VT fuse exemplified a broader tension in wartime science, the pursuit of technological elegance intertwined with lethal practicality. On the German side, attempts to understand the sudden change in Allied artillery effectiveness were hampered by intelligence limitations. Reconnaissance teams noted patterns in the strikes, but could not determine the underlying technology. Some reports speculated about improved artillery training or new firing techniques, but the concept of a radar-triggered shell seemed impossible to German engineers at the time. By mid-January 1945, the cumulative effect of VT-equipped artillery had disrupted multiple German units, contributed to the stabilization of the Allied lines, and accelerated the depletion of enemy morale and combat effectiveness. The human dimension of the VT fuse extended beyond immediate casualties. Soldiers on both sides adapted their behaviors in response to the technology. For American artillery crews, confidence increased. They could operate under extreme weather and terrain conditions with the assurance that their shells would find the enemy. For German infantry, fear and uncertainty became constant companions. The invisibility of the threat created a form of psychological attrition, where even surviving soldiers reported higher stress, reduced cohesion, and hesitation to advance. These effects, while intangible, were as strategically significant as the material destruction caused by the fuses. At the strategic level, the success of the VT fuse in the Ardennes informed subsequent Allied operations. Commanders recognized that airburst artillery could compensate for shortages in manpower, artillery, and aircraft. Smaller units could achieve disproportionate effects when equipped with advanced technology. Planning for offensives began to incorporate the assumption that VT artillery could be used to shape the battlefield, deny terrain to the enemy, and provide both offensive and defensive advantages. This integration of technology and tactics foreshadowed the post-war emphasis on precision-guided munitions and the broader use of science as a force multiplier in military strategy. The legacy of the fuse also extended to production and logistics. Factories adapted to the mass production of fragile VT shells, implementing rigorous quality control to prevent failures in the field. Special handling procedures were developed to transport the shells safely, and crews received detailed instruction on loading and maintenance. The combination of innovation, rigorous engineering, and disciplined execution became a model for future military-industrial efforts. It demonstrated that technical sophistication alone was insufficient. Successful deployment required seamless integration with training, command structures, and logistical support. As the Ardennes campaign drew to a close, historians would later note that the VT fuse was a pivotal factor in the Allied defense. While not the sole determinant of victory, its contribution was undeniable. It saved units from destruction, inflicted disproportionate casualties on enemy forces, and forced a rapid re-evaluation of artillery tactics. Memoirs from soldiers like those of the 38th Cavalry Squadron frequently highlight the fuse as a turning point in their personal experience of the battle. They describe moments where hope seemed lost, only for the sudden airburst of a shell to disrupt the enemy and preserve their position. These first-hand accounts underscore the fuse's dual nature as both a technological marvel and a profoundly human instrument of survival. In retrospect, the story of the VT fuse embodies a larger irony of warfare. The most decisive innovations are often invisible, overlooked, or constrained by bureaucratic caution until necessity forces their use. A small component inside a steel shell, engineered with precision and ingenuity, altered the calculus of battle, changing both the material and psychological landscapes of the battlefield. It demonstrates how human ingenuity, applied under extreme conditions, can transform the course of events, often in ways that no strategist, planner, or soldier could fully anticipate. The months after the initial deployment also revealed broader implications for Allied planning. By the spring of 1945, VT-equipped artillery had become standard in European theaters, influencing decisions about troop movements, concentration of forces, and offensive timing. Commanders could allocate fewer resources to artillery barrages without reducing effectiveness, freeing manpower for other critical operations. This efficiency contributed to the acceleration of the Allied advance into Germany, compounding the technological advantage of a single, carefully guarded innovation. For the engineers and scientists behind the fuse, the war's end did not diminish the significance of their work. The principles developed in the VT program: ruggedized electronics, miniaturized radar, shock-resistant circuits, would influence post-war military technology, from guided missiles to air defense systems. Their achievement illustrated a central lesson. Breakthroughs often emerge not from grand strategies alone, but from meticulous problem-solving applied to a specific, narrowly defined challenge. In this case, the question of when and how an artillery shell should explode. The solution: reshaped battlefields, preserved lives, and left a legacy that extended well beyond the war. Yet, the human cost remained profound. Even as the VT fuse saved Allied lives and disrupted German operations, it also inflicted suffering at a scale that could not be quantified merely in strategic terms. Soldiers on the receiving end faced lethal forces they could neither predict nor escape. The airburst, a technological triumph, was also a grim reminder of the war's indiscriminate destructiveness. In this duality, a marvel of human ingenuity and an instrument of death, the fuse exemplified the complexity of technological advancement in wartime. The psychological shift induced by the fuse extended to leadership at all levels. Junior officers and enlisted men alike had to trust that technology would perform as promised under extreme conditions. This reliance on invisible, unseen forces marked a departure from traditional combat experience, where success depended largely on physical positioning, fire discipline, and human judgment. The fuse represented a new axis of uncertainty and control. It could simultaneously reduce risk for those who wielded it and magnify fear for those who faced it. As historians reconstruct the Ardennes campaign, it is clear that the VT fuse contributed to a profound irony of the war. A weapon initially restricted due to fear of technological compromise became decisive precisely because officers were willing to use it in defiance of bureaucratic caution. The most powerful effects arose not from mass production or doctrinal planning alone, but from human initiative, the courage of a commander to deploy an overlooked technology when lives hung in the balance. In doing so, they revealed a fundamental truth of innovation in warfare. The intersection of science, leadership, and timing can achieve results far beyond what any one element could accomplish alone. By the spring of 1945, the Ardennes campaign had ended, and the Allies were pressing relentlessly into Germany. The effectiveness of the VT fuse had become apparent not only in military dispatches, but in the personal recollections of soldiers who had experienced its sudden and terrifying impact. For the artillerymen who had operated these rounds, the war had become a test of precision, discipline, and nerve. For the infantrymen who relied on artillery support, the fuse had been a lifeline in moments of near-certain annihilation, and for the German soldiers who faced it, it had been a harbinger of a new kind of warfare, invisible, unpredictable, and psychologically devastating. The immediate aftermath of the Ardennes revealed the fuse's profound strategic consequences. Casualty reports indicated that VT-equipped batteries inflicted far higher losses on German infantry than conventional artillery. Units attempting frontal assaults on positions defended by these shells often suffered disorganized retreats, leaving armor unsupported and supply lines exposed. Though historians cannot quantify every indirect effect, the combination of material destruction and psychological attrition was unmistakable. German planners, even those removed from the front, recognized that the threat of these airburst shells had changed the rules of engagement. By the time the Allies crossed the Rhine, the once feared Wehrmacht infantry had learned to fear artillery not merely as a physical force, but as a judgment from an unseen hand. In Washington, the engineers and scientists behind the VT fuse followed its deployment closely. Memoranda, letters, and declassified technical reports reveal their pride and apprehension. They were proud of a solution that had overcome what had seemed insurmountable mechanical and electrical obstacles, yet they were also conscious of the moral weight of their achievement. Unlike conventional weapons, the fuse's design did not merely increase accuracy, it transformed the very character of combat. Engineers such as Robert Broad wrote later about the duality of their work. The exhilaration of solving a complex technical problem was inseparable from the recognition that each solution produced lethal consequences. The fuse's success was, in their words, a triumph of ingenuity, shaded with the gravity of human cost. At the operational level, commanders began to reconsider traditional artillery doctrine. Before the introduction of proximity fuses, effective barrages relied on volume and sequential firing. A battery could saturate an area, but enemy troops had time to react, seek cover, or disperse. With VT rounds, simultaneous firing from multiple batteries became not only possible, but tactically optimal. Forward observers could call coordinates with confidence that the shell would detonate near the target. The psychological effect on enemy troops was profound. Accounts from German veterans recorded after the war describe a mix of awe and terror. They had no precedent for artillery that could detonate above them with such precision, and the unpredictability of the strikes eroded morale and unit cohesion. The soldiers who survived the Ardennes often remarked that it was the unseen threat, the invisible presence in the air above them, that imposed a greater cost than any visible explosion or gunfire. This transformation extended beyond the battlefield into broader military planning. The ability to neutralize infantry without massed assaults or protracted bombardment meant that smaller units could hold key terrain. Operational tempo increased as planners could allocate fewer soldiers to securing positions already defended by airburst artillery. The psychological pressure created by VT-equipped batteries allowed commanders to dictate the pace of engagements in ways that had previously been impossible. In essence, one small piece of technology reshaped strategic thinking, demonstrating how human ingenuity could multiply the effect of conventional forces. Yet, the story of the VT fuse is not only one of technological innovation, it is also the story of individual decisions under uncertainty. Colonel Axelson, for example, had acted in defiance of strict regulations, prioritizing the lives of his men over bureaucratic caution. His decision to deploy the shells without explicit authorization exemplifies a recurring theme. In military history, the tension between adherence to protocol and the exercise of judgment in moments of crisis. Without such initiative, the fuse might have remained an untested curiosity, hidden in bunkers and crates. Instead, it became a decisive instrument, influencing the outcome of battles and, ultimately, contributing to the broader Allied advance into Germany. The post-war analysis of the Ardennes campaign highlighted the fuse's influence in quantitative and qualitative terms. Studies conducted by the US Army and later historians compared casualty rates and engagement effectiveness between units with conventional artillery and those equipped with proximity fuses. Results consistently demonstrated a marked increase in both lethality and efficiency. Fewer rounds were required to achieve the same operational effect, and forward observers reported significantly higher rates of target neutralization. The fuse's impact was particularly pronounced in forested and built-up terrain, where traditional artillery relied on indirect fire that often missed dispersed or concealed troops. The airburst capability rendered such concealment largely ineffective, leveling the tactical playing field in favor of well-trained, technologically equipped units. Human narratives further illuminate the significance of the fuse. Memoirs of artillery crews recount moments of intense concentration when the success of a firing mission hinged on precise calculations and careful adherence to procedure. Soldiers remembered the tension of loading fragile shells, double-checking settings, and monitoring environmental conditions that could alter trajectory. For the infantry, recollections of being saved by sudden bursts of shrapnel falling from above became part of their personal war stories. German accounts, in contrast, describe a form of combat stress that defied conventional understanding. The disorientation of facing a lethal threat that could not be anticipated, the sense of helplessness in a world where training and experience offered little protection. The psychological shift extended to the perception of warfare itself. The VT fuse exemplified a broader transition in military history, the increasing role of technology as a decisive factor, capable of reshaping both material outcomes and human experience. Traditional metrics of force, troop numbers, artillery density, armor strength, were no longer sufficient to gauge battlefield potential. Innovation, engineering, and the human capacity to deploy complex technology effectively had become central determinants of victory. The fuse, though small and physically inconspicuous, represented a profound conceptual shift. The weapon itself was not only a tool of destruction, but a mechanism for altering perception, morale, and decision-making on both sides of the front. The post-war careers of those involved in the VT program illustrate the enduring influence of their wartime work. Many engineers transitioned into roles in the emerging fields of guided missiles, radar, and precision munitions. Lessons learned in ruggedizing vacuum tubes, managing high-acceleration electronics, and integrating complex devices into mass production contexts informed the development of Cold War-era technology. The principles underpinning the VT fuse, miniaturization, durability, and reliability under extreme conditions, became foundational to modern military engineering. In this sense, the fuse's legacy extended far beyond its immediate tactical effects, shaping the trajectory of military science for decades. Despite the technical focus, the human dimension remained central. Soldiers who experienced the fuse firsthand often reflected on the thin line between life and death. One artilleryman recalled the moment a German counterattack was halted within minutes by an airburst. "I saw men running into the trees, thinking they were safe, only to be cut down by the very sky itself. It was terrifying. Yes, but it saved our company from destruction." Such accounts capture the duality of technological innovation in warfare. It magnifies both human vulnerability and human ingenuity, reshaping the experience of battle in ways that raw statistics alone cannot convey. Historians today continue to emphasize the fuse's role in reshaping the final months of the European theater. While not the sole factor determining victory, it served as a critical enabler of Allied operational success. Its deployment exemplified the combination of scientific ingenuity, disciplined execution, and human initiative that characterized the most effective military innovations of the Second World War. The fuse's story underscores a recurring pattern in history. Transformative tools often emerge from the intersection of necessity, creativity, and calculated risk. In reflecting on the VT fuse, one cannot ignore the profound irony it embodies. A weapon developed in secrecy, initially restricted due to fears of technological compromise, became decisive because human judgment overcame bureaucratic caution. Its greatest effects arose not from mass production alone, but from the willingness of individuals to act decisively in moments of uncertainty. Colonel Axelson's choice to fire without explicit authorization, the engineers' relentless pursuit of a solution to seemingly insurmountable technical problems, and the artillery crew's meticulous execution all combined to transform an overlooked innovation into a war-winning force. In this convergence of technology, leadership, and timing lies a broader lesson about the nature of human ingenuity under pressure. The story also invites reflection on the psychological dimensions of warfare. The VT fuse created fear that was as potent as its physical effects, altering enemy behavior and forcing a re-evaluation of entrenched doctrines. Soldiers who had relied on training, experience, and discipline found themselves confronting a threat that could not be countered by conventional methods. In doing so, the fuse highlighted the enduring importance of perception, uncertainty, and adaptability in combat. Victory was not only a matter of firepower, but of understanding and exploiting the human response to new, unforeseen challenges. As the war drew to its conclusion, the VT fuse stood as a symbol of what was possible when human creativity and scientific knowledge were applied to urgent, real-world problems. It demonstrated that the smallest components when engineered with precision and deployed with judgment, could have outsized effects on the course of history. From the snow-laden forests of the Ardennes to the planning rooms of Allied headquarters, the fuse reshaped the battlefield, saved countless lives, and introduced a new paradigm in military operations. Ultimately, the story of the VT fuse is more than a tale of technological triumph. It is a story about the interplay of human decision-making, ingenuity, and moral responsibility in the midst of unprecedented violence. It is a narrative that intertwines the personal and the technical, the immediate and the long-term, revealing how one overlooked innovation could turn the tide of battle, reshape military doctrine, and leave a legacy that extended far beyond the guns and soldiers who first wielded it. It reminds us that history is often determined not solely by grand strategies or vast armies, but by the convergence of subtle innovations, decisive choices, and the courage to act in the shadow of uncertainty. The fuse, small and unassuming in its steel casing, became a silent witness to the complexity of human endeavor in war. It captured the essence of a profound historical irony: that an overlooked, secretive component could produce consequences more decisive than the mightiest tanks or the heaviest artillery barrages, and in doing so, it transformed not only the immediate course of the Second World War, but also the way generations of military thinkers, engineers, and soldiers would understand the relationship between technology, psychology, and the conduct of battle. Its legacy endures, a testament to the power of ingenuity and the often unseen forces that shape history. Even decades after the guns fell silent, veterans of the Ardennes campaign would recall the VT fuse not only as a weapon, but as a defining presence in their memory of the war. Letters, diaries, and oral histories reveal that its effect lingered long after the battle ended. Infantrymen described the surreal experience of seeing German soldiers struck seemingly out of nowhere. The sudden flashes and shrapnel bursts transforming familiar terrain into an unpredictable landscape. Artillerymen spoke of the meticulous calculations and careful handling that went into each shell, remembering the responsibility that came with wielding a weapon so precise, yet so devastating. The fuse demanded attention, discipline, and respect. A single misstep could waste its potential, or worse, endanger friendly forces. For German soldiers, the psychological toll was equally profound. In post-war interviews, many admitted that VT shells instilled a fear that no training could erase. One former Wehrmacht officer recalled standing in a snow-drenched field, hearing the faint whistle of shells above him, and realizing that cover was meaningless. Units that had once advanced with confidence found themselves breaking under pressure, even when facing a smaller number of American forces. The fuse's unseen threat forced German commanders to reconsider tactics, slow advances, and disperse formations, all outcomes that favored the Allied defenders and hastened the collapse of their Ardennes offensive. Beyond the battlefield, the success of the VT fuse influenced post-war military doctrine worldwide. NATO planners and emerging Cold War strategists studied the Ardennes as a case study in the integration of technology and human decision-making. The lessons were clear. Even a small, ingeniously engineered device could shift the balance of power if deployed with foresight and tactical understanding. The fuse's design principles, miniaturization, robustness under extreme conditions, and reliable functionality in a wide range of environments, became foundational concepts in the development of guided munitions, missile warheads, and precision artillery in the decades that followed. Its legacy persisted not only in hardware, but in the mindset of military engineers who came to appreciate that innovation and initiative often mattered more than brute force alone. The human-centered aspect of the story remained equally important. While the VT fuse exemplified technological ingenuity, it was ultimately human judgment that determined its impact. Colonel Axelson's decision to authorize firing without direct approval, the meticulous care of artillery crews, and the ingenuity of scientists who transformed theoretical circuits into combat-ready devices all converged to produce a decisive effect. The Ardennes campaign serves as a reminder that innovation alone is insufficient. The application of knowledge, courage in decision-making, and disciplined execution are what transform a tool into a weapon capable of altering history. In the final analysis, the VT fuse represents more than an engineering triumph. It is a testament to the interplay between human creativity and the unpredictable realities of war. Its story underscores the irony of history. A small, overlooked piece of technology, once confined to secrecy and skepticism, became a decisive factor in the largest land battles of the European theatre. From the perspective of soldiers, engineers, and historians alike, the fuse stands as a silent witness to the complexity, ingenuity, and profound consequences of human endeavor in times of conflict. Its legacy continues to shape our understanding of how innovation, risk, and human judgment converge to alter the course of history in ways both immediate and enduring. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.